Welcome everybody to this tutorial video on OxTS Georeferencer. So over the next 20-25 minutes, we'll be just going through Georeferencer, seeing all the new features that we're releasing, and also showing you exactly how to use it and how to get the most out of it. So I'll be taking you through the different files that you need for your different LiDAR devices that are compatible with Georeferencer, and also how you can check your surveying route, and also all of your processing options that Georeferencer offers to get you the point cloud that you want exactly. I'll also demonstrate our bore site calibration feature, and of course the georeferencing point cloud creating feature. And then I'll show you some point clouds at the end and how those different options and features really play into those point clouds. So this here is Georeferencer, as you can see. This is the Files tab, and I'll just start by taking you through which files you're going to require to make a point cloud. So here you can see just got some data prepared. So we're going to be looking mainly at this data set here. And so you can see there are 5 files, and so we can just drag these straight into Georeferencer, and I'll just explain each one of these. So you've got, first of all, the LiDAR file. So this is taken with a VLP16, and this LiDAR file is in .lcom format. .lcom is our own format. It's essentially exactly the same as a .pcap. pcap would be more common. LCOM, the difference is simply that the LiDAR data was logged directly onto our INS. So our INS devices are capable of logging LiDAR data up to 16 laser LiDAR units. So that's what we've done here. We've got this LCOM, and Georeferencer works identically for LCOM and for PCAP. And then we've got the navigation data. So this is an NCOM file, and we've also got a VAT, which is a configuration file that you get from the navigation data. So I'm assuming if you're watching, you are somewhat familiar with our INS devices. So the idea would be that you go out and you record your navigation and LiDAR data, you get back for post-processing, and you would get the RD file off of your INS device, and then you can use our NavSolve software to process it. So you would get a folder from NavSolve that looks a bit like this. In it, you'll find a lot of different files, including that RD that you took off the unit. And in here, you would have an NCOM, which is the final navigation data file that you'll want to be using for Georeferencer, and also the VAT. So these 2 files simply in here, and you would just use those in Georeferencer. So the other 2 files that we have are a LIP and an LIR file. So that might sound a bit esoteric, but these are extremely simple, just text files saved as .lip or .lir. And if I open them up, you can see extremely simple. These are just 3 numbers. The idea with these 2 files are your configuration between your INS and your LiDAR. So I will show you in a second our hardware tab, which will show you the configuration. But these numbers essentially will just give those values into Georeferencer. So these are the angles between the LiDAR and the INS setup, and these are your linear displacements. So you can see on here that we have a map, so you can see where you've been driving or flying, whatever it might be, and you just need to double check that this is the file that you're expecting for the navigation data, and that your LiDAR data matches that. So you can see here what we've done is driven around on our airfield in a few circles. So this is for a bore site calibration run. Essentially, the idea is that we drove around our reflective targets, and we're going to calibrate our INS to LiDAR setup. So second thing to do is to choose which LiDAR you're using. So you've got a list of LiDAR that Georeferencer is compatible with, and you just need to select the one that you're using. So this was VLP16. And we can now take a look at the hardware. But before I do that, I just want to show you a variation on this, which is with some OxTS data. So with OxTS data, the process is exactly the same as I've showed you here, except you need an additional .json file. So if you're familiar with OxTS LiDAR, you'll know about the JSON file that is used to configure the unit, and this will give you elevations and azimuths of the lasers in the LiDAR unit. And you don't need to drag this into Georeferencer, but you do need to save it in the same folder as your PCAP with the same name. And if you do that, Georeferencer will find it, and it will be georeferenced correctly. So if we now have a look at the hardware configuration tab, you can see a model of the setup. So what we have done is we've used a mount that we use internally at OxTS, which holds an XNAV INS device and a VLP16 LiDAR together. And you can see this here. So the blue cube being the LiDAR. You can see here the LIP and the LAR values that we've used. So these are the same values in those text files. And in here, if you wanted to, you can edit those just to make sure that you've got it right. So something that can be tricky is to get the angles correct. This is simply done. You can use these axes to make sure you're getting the angles between the INS and the LiDAR correct. So these would be detailed in each LiDAR's manual. These are different for different LiDARs, but you can just use the manuals, and this hardware tab should help you to get that right. So if I just go back to the Files tab, I'm just going to show you the processing options that you have. So in here, processing options, you've got a few different things you can select and choose. We've got georeferencing options on the left. We've got bore sighting options on the right. So if you know about Georeferencer, you know that it's used for two main purposes. One is to create point clouds with your LiDAR and navigation data. And the other is to calibrate your LiDAR to INS setup before making a point cloud. So we've got bore site calibration options, and we've got georeferencing point cloud creating options. So there are more options, which we detail in a support article, which require an advanced command to use. But these ones are more common ones. So you can see on the left here, you've got reflectivity threshold. So LiDAR data will record an intensity of reflection in the data usually, and here you can choose between 0 and 255 what value you would like. So if you wanted a smaller point cloud, or you only wanted to see highly reflective points, you would put in, say, 100, but the default would be 0. So I thought I would show you guys an example now of what that actually means. So here is a point cloud. I've added some shadow on it just to give it some definition. And this is a full point cloud, so this would be georeferenced at 0 here. But if I were to georeference it now at 100, you can see if I show you the intensity scalar field, what you would essentially be doing is editing out these points. So you can see as I increase this reflectivity threshold, you're only seeing the more reflective points. So if I now zoom in, so this is where we've driven actually on our airfield here. So we've driven around in these circles. You can see the hangars that you're just seeing. And we've driven around some reflective targets that we're going to use for site calibration. These are these two square targets. And we've got also some reflective strips on the airfield. So that's what you're seeing there. And you can choose to edit this in point cloud editing software like this, or you can do it in Georeferencer. So going back, we've got a minimum range and a maximum range. So minimum range is particularly useful if you've done a survey, say on a car of some kind, and you had the LiDAR was viewing the car, say like the corner of the car or the bonnet of the car, and that was getting into the point cloud everywhere you went. Obviously that's not ideal, and so you could just increase the minimum distance to 2 or whatever to make sure that doesn't happen. Similarly on a UAV, if you just put it on put the LiDAR on the UAV without restricting the field of view, you could edit out any LiDAR points that are hitting the UAV just by increasing this minimum range. Another option is error threshold. So this is a new one. It's quite exciting. So what we have done is used a sophisticated formula to work out the centimeter precision that all points in a point cloud has. And you can choose to, say, select 10 centimeters for this error threshold. And what that will do is only write points into the point cloud that are accurate to 10 centimeters or better, or whatever accuracy it might be. So if I now show you another example. So we've got this village survey, or rather we've driven through a village, and we've got to this section here. And so what we've done is we've encoded into this user data scalar field the precision of points, and you can see that the road is in blue, which indicates it's the most accurate because it's closest to the INS, and you can see it gets green and then yellow. So the further away you're getting from the INS, as you would expect, the less accurate it gets. But also you can see where we've driven through this village, and when trees or buildings are getting in the way of GNSS, the INS is going to lose some accuracy. And you can see here where there are trees blocking the way, you can see it was doing okay, and then the longer it went without GNSS updates, it was getting less and less accurate. And you can see this straight in the data. So something you can do is choose in Georeferencer to edit out inaccurate points if you wanted to, or you can keep them here. You can now edit them out here. So for example, I can simply edit out inaccurate points. So you can see exactly where you might want to resurvey if you wanted to do that, or just ensure that you've got the highest accuracy points and none of the rest of the point cloud is being affected by those. So a few options over on the bore sighting. So we've got a number of iterations. So the boresight process will typically find values that it converges towards, and the more iterations you're going to do, the longer the process will take, but generally the more accurate it will get. So that would be in the optimization iterations. So default was 200. Target detection iterations, so I'll show you what that means later on. Reflectivity threshold, so this is exactly the same as over here. The thing is, different LiDAR can be differently calibrated. So often LiDAR will have the value of 100, so it's between 0 and 255, and a value of 100 would be retroreflective, which would be essentially maximum reflectivity. So if we look at those targets again that we saw and the reflective strips, so these would typically be at 100 and everything else wouldn't be there. But some LiDAR are not calibrated exactly thus, so you can just increase that or decrease that to whatever it might be. You've got also options for minimum and maximum range. So minimum range, again, if you are viewing your vehicle, you don't want that to be in there. Maximum range, so you might want to decrease this, particularly if you're surveying typically at, say, 20 meters. You don't want points, say, from 50 meters, pulling away the calibration values, because the further away you're looking from the INS, the less accurate those points are. Okay, last thing, actually, we have a new feature which is in beta. So our boresight calibration process, when we first released it, would optimize your LIR. So the LIR being these angular values between your INS and your LiDAR. But we now have in beta a new feature which will optimize your LIP values, which are those displacements. And so if you calibrate both LIP and LIR, you have the maximum flexibility in your setup. So now if I just take you through a boresighting process, which is extremely simple. So again, we've driven around our targets, and now you're going to see how we can use that to calibrate our setup. So what the software will be doing now is screening that LiDAR data to find only and all those retroreflective points. So what we want to do is have a look at the targets and nothing else in the point cloud. So if we can isolate those, we can just look at the targets, and then the software will calibrate the setup by trying to get a best fit of the targets onto what they should be in reality. So depending on how beefy your computer laptop is, this can take a few minutes and only needs to be done once with your setup. So if you did leave your INS and LiDAR on your vehicle, you wouldn't need to be doing boresight calibration every time you go out and survey. So you can just boresight your setup once and use those values that you get to process, to georeference your point clouds from then on. So in terms of user input, the boresight process is extremely simple. So you just need to do, as you can find in the boresight calibration brochure that we have on the website, the process manually is to just drive around these targets for a couple of minutes. And then in terms of software use, you can now see on here that it's screened the point cloud for those same retroreflective points. So you can see those targets that we were just seeing here and those strips. And you can also see where we've been driving in gray. And so the software now just wants us to prompt it to tell it where exactly those targets are. And then it wants us to make sure that only the target retroreflective points are in these blue circles and nothing else. So we can make these smaller or larger, whatever it might be. And we then just choose the altitude that these are at. So usually just select the center of the bell curve here. And you've selected exactly where those targets are. So if we check the number of points, as you can see, a good number, 70,000 points on these targets. Continue the bore site. And then this will be where it's doing this convergence process to calibrate these. So you can see on the left here, what we've got is an azimuth range hit count. Essentially what that is a graph of the distance away that you're seeing points from the LiDAR and also at what angles. So you can imagine, I think what we did was on this one, we would put the LiDAR on the back of the vehicle, on the back window. So you've got about 90 degrees where the LiDAR is just seeing sky, and so you're not getting any points here. And then all the other angles, you can see it's getting hits around 0 to 20 and then 30 meters. And this is what you would aim to get. So you want to be viewing those targets from a range of typical angles and distances that you would expect to survey at. And so now if we just click view the comparison, you can see what we've got before and after. So we didn't select the LIP calibration, so the displacements have remained the same, but the LIR has been optimized to change these angular values. And so this would make quite a big difference. And finally, what you can just do is to click Run Georeferencing. And that's the final thing that Georeferencer offers. It doesn't require any more user input than that. You just click on that and you will get, it will take some time because LiDAR data is very big, but you will get a point cloud out the other end. So if we now have a look at some example point clouds, so we've got an example here of bore-sighted and unbore-sighted data. So you can see the big difference that bore sighting can give you. You've got a lot of smearing that happens when it's unbore sighted, and then it's perfectly square and planar when it's been bore sighted. And you can see even these strips, you're getting double vision in the unbore sighted, but they're exactly as they should be when they're bore sighted. So if we look again, just remind ourselves of the error threshold feature. So you can view that in any data that you might want. So we can view the error threshold data in this one. And you can see again that the hangers are the least accurate, and we could edit those out if we wanted to, or whatever it might be. So that was our georeferencer tutorial. Thank you for watching, and I hope you enjoyed.